The next question is, what is an eigenvalue? So, for the calculating the eigenvalue for each of the principal components, what we need to do first is to project all the observations to the principal component. So, for PC1, or principal component 1, we are going to project all these observations, and then what we do is to calculate the distance between the origin and those places where these observations were projected to in the principal component. And we do the same with all the values. So you're going to have these values here. They will be negative because the values will be lower than 0, and these ones will be positive, lower than the mean, and these ones will be positive because they will be higher than the mean. So, and then when we add those values, when we add negative and positive, they cancel each other out. And in order to solve, we already seen this trick when we calculate the variance and sum of squares, is we square the values before we add them, because when we square the values, the positive values remain positive and the negative values become positive. So they measure that we will have it measures very well the distance, and it doesn't have the problem of having positive values and negative values that cancel each other out. So when we add the squares of those values, that is the eigenvalue of the principal component 1. And we do the same for principal component 2, but we need to project all these observations to principal component 2. So this one goes here, this one goes there, this one goes there, this one goes there, and so on and so forth. Now, then once we have these projections, then we calculate the difference between the value of in principal component 2 and the origin, and the same here. So what we are going to have positive and negative values, and we square them and we add those values. And you can see that the distance of the observations again from the origin is not as large as in PC1. So the PC2 will have an eigenvalue that is lower than that of PC1. Next question is, what are factor or component loadings? Okay, so when we have the principal component, and it's as I mentioned before, is similar to a regression line. But it's different the way that we calculate the distance of the observations to the line. But we can determine how much. So we take any value of PC1, but we can take the most extreme, which is this value, for example. And then we calculate the distance between the origin and that value, and then we do from that value the distance from this horizontal line and the value of the principal component 1. So wherever we do that, the proportion of these two vectors or segments is always the same. If this is 2 times larger than this, which is not in this case, it will be the same at any point that we choose, right? Now, what we are interested in is in having those values, those distances, so choosing distances such as that we have this vector here to have a size of 1 unit. So when we have this vector that has the size of 1, then those values are the factor loadings. So we call this vector the eigenvector of principal component 1, and in order to specify the eigenvector, so we know that the length is 1, but we need to know this value and this value. So, and this will be some value because these are the sides of a rectangle with a triangle with a 90 degrees angle. These are the two sides, and this is the hypotenuse. So these two values are going to be lower than 1. So this is the factor loadings. So here we've got the terminology. So this one is the factor loading of item 1 on principal component 1, and this one is the factor loading of item 2 on the principal component 1, and this vector is called the eigenvector. So the component loadings or factor loadings are represented in when we use software in this way. We've got a list of items or variables and a list of principal components, and then we've got the loadings for each item with the components. Now typically there is a some values that are not presented, and that is arbitrary. We can indicate in the software which values we want, what was the threshold for values to be presented. Uniqueness, so is for each item, some of the variability on the values of that item is explained by the principal component, but some variability is not explained by any of the principal components, and so that's called unique variability. So the more you explain the variance by the principal components, the less uniqueness, and vice versa. Next question. How do eigenvalues relate to variation accounted by the principal components? Okay, so there is a simple formula. The variation for each principal component is calculated by the eigenvalue divided by n-1. So that's the variation. And then what we can do is to calculate the total variability of the data, and the total variability of the data can be captured by the variability of the principal components. So the total variability of the data is the variability of principal component 1 plus the variability of principal component 2. And in this simple example, we only have 2 variables, so we can only have 2 principal components. But if we add more variables, then we have more principal components. So the total variability will be the sum of the variability due to each of the principal components. So, and in percentages, the percentage variation of principal component 1 plus the percentage variation of principal component 2, in this case will be 100%. But sometimes when we have more variables, we have more principal components. So the total variability will be given by the variability of each, the sum of the variabilities of each of the components. But then in the model, we are going to keep a couple or three or more or four, but we don't keep all the principal components. So when we keep these four, let's say 4 components out of 10 variables, so those components will not explain the whole variability of the data. They will explain a huge percentage of the variability of the data. So in that case, we will have the sum of the components, of the variabilities of the components that are presented in the output. It will not add up to 100%. But that's because we are not presenting all the components, and that's because we want to do data reduction. We want to have less components than the variables that we started with. And this is a way of presenting what I've just explained. We've got the principal components that they remained after the removing the components that we don't want to keep. And we've got the eigenvalue. So in this case, and it's always the case, that the first principal component will have a higher eigenvalue, and the second one will be the second eigenvalue. And then the proportion of variability explained by that principal component 1 is 50%, and the amount of the proportion of variance explained by principal component 2 is 18%, and the cumulative is 68%. And as you can see, these two components only account for 68% of the variance. And we remove the other components. If we keep all the components, they will explain 100% of the variance. Next question is, what is a scree plot, and what is the main criterion to choose the number of components? So a scree plot looks like this. We've got the eigenvalue score and the components. And it's always like this. The first component is the higher eigenvalue, the second has the second eigenvalue, and the third, and so on and so forth. So one rule that is very popular to decide which components to keep in the model is that we remove all the components that have an eigenvalue lower than 1. So here the horizontal line shows the eigenvalue of 1, and the components 1 and 2 are above that line, and component 3 is just below that line, therefore it's eliminated. Another question: what is the difference between confirmatory factor analysis and exploratory factor analysis? The difference is that confirmatory factor analysis, instead of asking a software to find the best combination and number of factors or components, the factorial structure is provided and tested. So instead of providing the data and passively observing what the structure, what components are, and how each item loads to each component, instead of letting the software doing that, we as researchers have a theory about that. And typically that theory comes from, for example, in psychology, we use scales, inventories, that they claim that they have a factorial structure. that some items correspond to some factor, other items correspond to another factor. So we actually can give to the software that structure that we believe is true, and then what we do is to test, is that model that we have a good model of the data. So can it account for the variability of the data that we observe in our study? So that's the difference between exploratory factor analysis. We don't know the factorial structure, and we let the program give us the factorial structure. Confirmatory factor analysis, we do know the structure, and we give that to the program, and we ask the program to tell us whether that structure is a good account of the data or not.